Hi guys, this is Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland. And this short video, another video in our series of videos dealing with correlation and regression, is going to concentrate on the correlation formula, okay? And in particular different forms of the correlation formula, and the reason why I do this particular video is because I've heard so many times from students here at the National College of Ireland, and actually other students as well that have contacted me, and what I've heard is, oh, my lecturer doesn't use that particular formula, is there a problem with using that particular formula, and so on and so forth. So we come across these particular challenges when we're teaching this particular subject, and especially teaching it to students and supporting students in a classroom where we've had different teachers, lecturers teaching the particular topic. So all I really want to do is to try to demystify what's going on under the hood with respect to our formulas, and how to get from one formula to another is really what I want to really try to get across here. So let me just actually provide a definition first of all of the correlation coefficient. Okay, so we're just going to provide a definition. Okay, the definition for the correlation coefficient, and I'm not going to go into any detail here. Okay, in the previous video we rationalized with respect to this correlation coefficient, where we develop it from the covariance, and we look at its properties and so on and so forth. But a definition of the correlation coefficient, the sample correlation coefficient, more importantly. Okay, so this is our sample correlation coefficient, is that or is simply equal to the covariance. Is equal to the covariance of our independent and our dependent variable of x and y, normalized with respect to the standard deviation of x times the standard deviation of y. Okay, and this is the definition. Okay, where, and it's important maybe I say this, where the covariance of xy, the covariance of xy is the sample covariance, which is simply equal to, it's the cross products. Okay, so it's the sum of the x's minus the x bars. Okay, so it's the distance between the observations and their mean, the independent observations and their independent means, times the dependent observations and the dependent mean. So it's this value here. This is our cross product. Okay, relative, divided by n minus 1, because it's the sample covariance, and also on our standard deviation, where s of x, okay, our sample standard deviation, is the sum of the x's minus the x bar squared over n minus 1. And similarly in relation to sy is, well, it's the sum of the y's minus the y bars squared over n minus 1. So that's what we mean by our sample standard deviation for our independent variable x, and the sample standard deviation for our independent variable y. Okay, so this is the definition. This is the definition of our covariance. Now, there's many different formulas that we can have, and one formula that we have is that's being presented. I'm going to give three forms of the formula here. There's many different forms, yeah, but let's three frequently used forms of the formula. So let's say form 1. Okay, form 1 looks something like this. It's or is equal to 1 over n minus 1 times the sum of, where we have a normalization, x minus x bar relative to the standard deviation of x, times y minus y bar relative to the standard deviation of y. There's one form of the formula. And let's say we have form 2 of the formula. Looks something like this. It's or is equal to the sum of the x's minus the x bars times the y's minus the y bar. So it's the numerator from the covariance, okay, divided by, it's the sum of the x's minus the x bars, okay, squared. Okay, it's the square root of that, okay, times the sum of the y's minus the y bars to be squared, and it's the square root of that. Okay, so there's another form of the formula here that we have. And then finally form 3. So we have form 3, which is the version I actually like when it comes to calculations, is or is equal to n times sigma xy minus sigma x times sigma y divided by n times sigma x squared minus sigma x all to be squared, and it's that factor times n times sigma y squared minus sigma y all to be squared, and it's the square root of all of that, or the individual square root of each of the factors, okay, depending on which way you want to look at this. So we've got three forms. We've got form 1 of this particular equation. Okay, we've got form 2, and we've got form 3, and I want to try to rationalize how we get from here to here to here to here, so that there's no confusion. Okay, so let's just take our definition. Okay, let's just take our definition. And let's just expand out the definition by putting in what each particular term represents. Okay, so we know that the correlation coefficient R, so that we know that R is equal to the covariance of xy divided by S of x times S of y. Okay, what does that tell us? Okay, well, putting in the covariance, okay, I'm going to try to derive this form here. Okay, so just putting in the covariance, we end up with that R must be equal to, it's the sum of the x's minus the x bars times the y's minus the y bars divided by n minus 1. Okay, that's the numerator, which all needs to be divided by S of x times S of y. Okay, so just keep that in mind. Okay, well, now we have a division here by an n minus 1, so we can take that outside. Okay, so this becomes R is equal to 1 over n minus 1. Okay, times the sum of the x's minus the x bars times the y's minus the y bars all over S of x, S of y. Okay, now don't forget S of x times S of y. Okay, it doesn't matter which way we do this. It's S of x times S of y, or S of y times S of x. Okay, but this is like a fraction, so we can invert and multiply. So this is the same as R is equal to 1 over n minus 1 times the sum of the x's minus the x bars times the y's minus the y bars times S of x times S of y. Okay, that's the same thing here. Okay, and it doesn't matter which way we relate these two things here. The whole thing is divided by, the whole summation is divided by S of x, S of y, so we can actually divide the individual parts by it. So this is actually the same as R is equal to 1 over n minus 1 times the summation of, I can divide the S of x's into these guys here. So it's into x minus x bar over S of x times y minus y bar over S of y. Okay, actually, when we multiply this out, when we actually expand out the summation, yeah, this is actually this is actually the same thing here. So there's another form of the formula, and this is actually a nice form when we look at it, because this is actually talking about normalizing. We're actually normalizing the independent observations with respect to their mean and with respect to their standard deviation, and we're normalizing the dependent observations, the y's, with respect to their mean and their standard deviation. So this is like, if you think about it, it's like a Z transformation here going on here. So actually, what we end up with is normalized variables. Yeah, okay, that's one particular form. So that's our first form that we've talked about. What about the second form? Yeah, okay. So the second form looks something like this here. So how can we get here? Well, let's actually just take our definition again. So we know that R is equal to the covariance of xy divided by S of x times S of y. Okay, what do we know about that? Well, once again, we know that that must be equal to the covariance is the sum of the x's minus the x bars times the y's minus the y times the y bars. Okay, all over S of x, all over n minus 1. Okay, that's, once again, that's the numerator. And the denominator, okay, is, well, S of x is the sum of the x's minus the x bar squareds over n minus 1. Okay, and it's S of x, so it's the standard deviation, so it's the square root of that. Okay, times sum of the y's minus the y bars squared over n minus 1. Once again, it's the square root of that. Okay. Now, recall that the square root of a times the square root of b is the same as the square root of a times b. Okay, so in this particular case here, okay, well, I suppose excuse me, okay, I suppose actually recall as well that the square root of a over b is the same as the square root of a divided by the square root of b. So we can break this down here. So this becomes the numerator is x minus x bar times y minus y bar divided by n minus 1. That's our numerator. We haven't touched that just yet. Divided by, in this case here, this is the square root of the sum of the x's minus the x bar squareds divided by the square root of n minus 1, and that's to be multiplied by the square root of the sum of the y's minus the y bars squared divided by the square root of n minus 1. Now look what we have here. we have the square root of n minus 1 times the square root of n minus 1 gives us n minus 1. So what's happening here is that this particular let's say this particular term, or this particular part of the formula, okay, it's actually starting to reduce down. So actually this now is the numerator, which is the sum of the x's minus the x bars times the y's minus the y bars over n minus 1. Okay, is actually being divided by a fraction. Okay, it's actually the square root, okay, of the sum of the x's minus the x bars squared times the square root of the sum of the y's minus the y bars squared, all over the square root of n minus 1 times the square root of n minus 1 is the same as n minus 1. Okay, now this is the same as inverting and multiplying, so we actually have sum of the x's minus the x bars times the y's minus the y bars divided by n minus 1 times, we invert in this and multiply, which gives us n minus 1 divided by this term here, which is the square root of the sum of the x minus the x bar squareds times the square root of the sum of the y's minus the y bar squared. And you can see that these two terms here, the n minus 1's cancel, which leaves us with form number 2, x minus x bar times y minus y bar divided by the square root of the sum of the x minus x bar squareds times the square root of the sum of the y minus y bar squareds. That's form number 2. Okay, so this is form 2 of the equation. Yeah, actually, I suppose we could actually say form 2a would be, this is actually equivalent to x minus x bar times y minus y bar divided by the sum of the x minus the x bar squareds times the sum of the y's minus the y bar squareds, and it's the square root of all of that. So there's an alternative form there as well. Okay, that's a bar here, don't forget our mean. Okay? So this, let's say, is form 2b, and this is form 2a. Yeah? Okay, going back to our three forms now, we've done form 1, we've done form 2, and what we now need to get is the more difficult one, which is form 3. So how the hell do we get to form 3 of this particular formula? Okay, so to get to form 3, I'm going to take form 2, okay, of the formula. So let's just take form 2 and let's multiply it out. Okay, so let's continue okay, with form actually 2b. Okay, let's continue with form 2b and let's see how we get on. Okay, so let's see what we have. So form 2b is that or is equal to the sum of the x's minus the x bars times the y's minus the y bars all over, it's the sum of the x minus the x bar squareds times the sum of the y minus the y bar squareds, and it's the square root of that. Okay, it's the square root of all of that. Okay, so I'm just going to take the numerator first. Okay, let's have a look at the numerator and let's see what we can get from the numerator. Okay, so looking at the numerator, we have, that's the sum of the x minus the x bars times the y minus the y bars. Well, let's expand that out. Okay, what's that give us? Well, that gives us, it's the sum of x times y gives us our xy's, x times y bar, x times minus y bar gives us minus x y bar, and a minus x bar times a y is the same as a minus x bar y, and then minus times minus gives us a plus, and x bar times y bar gives us an x bar y bar. Okay, so that's what we end up with here. Okay, which is the same as, it's a summation of all of these. So it's a summation of all of these terms, this whole term here, which is made up of a summation of terms. So a summation of a summation is the same as a summation in total. So this becomes the sum of the xy's plus the sum of minus x times y bar, which is the same as minus the sum of x times y bar, minus the sum of x bar times y, plus the sum of x bar y bar. Okay. Now, don't forget, this index is from I is equal to 1 to n, so this is over the n observations. Okay, so n observations, keep that in mind. Okay, so we have n observations. So actually, the n of these summations in there. Yeah, okay, the n of these, the iterator goes from 1 to n. Okay, so when we have a look at that, okay, let's see. Well, we're going to keep this the way it is. The sum of the xy's is fine. Okay, don't forget we're trying to get to form. We're trying to get to form 3, okay, which is in sigma notation form. So I actually want to get rid of these x bars, if that makes sense, yeah? Okay? But let's think about it. This is the same as the sum of the xy's minus the sum of the x's times the y bars minus the sum of the x bars times the y's plus, now, the x bar is a constant, the y bar is a constant, and I'm going to sum these up over n things, so there's actually going to be n of these. So this is plus n times x bar, y bar. That's what that summation comes out to be. Okay. Now what about these things here? Okay. Well, let's think about this here for a moment. Yeah. Okay. Y bar. Okay. Or sorry, x bar. Okay. X bar is the sum of the x's. Is simply the sum of the x's over n. Okay. The sum of the x's over n. Sum of the x's over n. So therefore, okay. Therefore, we have that the sum of the x's must be n times x bar. If that makes sense, yeah, or whichever way you want to do this, yeah. Okay. So looking at this here, we can do a substitution here for these two particular terms. So let me just do that here. Okay, let's take that substitution. Okay, let me just get another piece of white paper here, just so that we're not getting overwhelmed by the light that's coming through here. Okay, so let me just take this and let me just put that here. Okay, so let's say, okay, so I'm going to make a substitution now. Okay, well, let's just take this form here. Okay, let's just take this line. Okay, so it's equal to the sum of the xy's minus the y bar is constant, so it can be taken out. So it's y bar times the sum of the x's. Okay, minus, in this case, x bar is constant, so it's minus x bar times the sum of the y's. Okay, plus n times x bar y bar. Okay, if that makes sense. Okay, that's what we end up with here. Okay. Now, the sum of the x's is the same as n times x bar. The sum of the y's is going to be the same as n times y bar, so this actually becomes the sum of the xy's minus n times y bar x bar, because sum of x's is n x bar, minus x bar times, well, minus n times x bar times y bar, okay, because the sum of the y's is n times y bar, plus n times x bar y bar, which gives us, this is the sum of the xy's minus 2n times x bar y bar plus n times x bar y bar, which gives us the sum of the xy's minus, we have minus, in this case, it's minus n times x bar y bar. Okay, and let's convert these back into sigma notation. This gives us the sum of the xy's minus n times the sum of the x's over n times the sum of the y's over n, and one of our n's cancels out, and if we get a common denominator across here, this gives us n, common denominator is n, so this gives us n times the sum of the xy's minus the sum of the x's times the sum of the y's. Okay, so that's our numerator. Our numerator is done there. Okay, let's just keep that done there. Let's keep an eye on that particular numerator, and let's have a look at our denominator. But actually, in this case, let's have a look at this. Let's have a look at this part of the denominator. Let's consider what we have is the sum of the x minus the x bar squareds. Okay. Well, that's the same as the sum of the x minus the x bars times the x minus the x bars. Expanding out, that's the same as the sum of the x squared terms. X times x is x squared. X times x bar gives us minus x bar. And x bar times x, again, is going to be a minus x bar. So we actually end up with minus 2 of them. Plus, we have an x bar to be squared. Okay. So actually, summation of summations is the same as summation. So this is the same as the sum of the x squared terms. Okay. Minus the sum of 2x times x bar plus the sum of the x bar squared terms, if that makes sense. And let's keep in mind here that the 2 and the x bars are constant, so so 2 and the x bars multiplied by every single x, so it can be taken outside. So that becomes the sum of the x squareds minus 2x bar times the sum of the x's plus the sum of the x bar squared terms, if that makes sense. Okay. Keep an eye on that there. And what do we get here? Okay, inside here we have well, what does this look like? Okay, this is going to be, well, this is the same as, isn't it? This is the same as the sum. This is the sum of the x squareds and we know that x is the same as, what's x the same as? The sum of the x's is the same as n times x bar. So this becomes, let's see here. Have I missed? Oh, I've missed a summation here. There's my summation. Yeah. Okay. The summation is the same as n times x bar. So this becomes minus 2 x bar times n x bar, because that's what the sum of the x's is, plus the sum of the x bar squared terms, okay, which is going to be the same as the sum of the x squareds minus 2n x bar squared plus the sum of the x bar squareds, okay, the x bar squareds square terms, okay. Now, let's keep in mind here that the x bar is the same as sigma x over. Am I missing something here? Okay, that the x bar term, okay, we have it's the sum of the x bar square terms here. Okay, well, when we actually there we go. When we sum them up, they're all constants. There's n of them, so this becomes the sum of the x squareds minus 2n x bar squared plus. There's n of these constant. X bar is constant, square is constant, so the sum of them is going to be n x bar square terms. And there we go. We have negative 2n of them here, and we have n of them here. So this becomes the sum of the x squareds minus n times the x bar squared terms here. Okay, and if we think about it from a sigma notation perspective, okay, that this is n times some variable, okay, n times some variable, which is the mean here, okay. It's to be squared. So if we go back into sigma notation, well, what's x bar? X bar is sigma x over n. So this just becomes the sum of the x squareds minus n times the sum of the x's over n to be squared. And we're nearly there. Just bear with it here for one more moment. Okay, it's a long video, I know, but we're doing a lot of these different forms of these equations here. Okay, so then what we end up with is the n, that's n squared here, if that makes sense, when we square it, and there's an n here, so they cancel out. So this actually becomes the sum of the x squareds minus the sum of the x's all to be squared over n. When we get the common denominator here, this is n sum of x squareds minus the sum of the x's all to be squared all over n. Okay, so this is the form now for this sum of squares with respect to the x's. Okay, and ditto, okay, with respect to the y's. With respect to the y variable, we must have that the sum of the y minus the y bar squareds must be equal to n times the sum of the y squared values minus the sum of the y's times to be squared all over n. So now we take our three pieces, this, and our previous piece here, okay, and we put them back into our formula. Okay, so don't forget where we started. Okay, here's where we started. Here's our formula. Okay, so we have or is equal to the sum of the x minus the x bars times the y minus the y bars all over the sum of the x minus the x bars squared times the sum of the y minus the y bars squared, and it's the square root of that. Okay, and that's equal to, we've done the numerator. The numerator, we worked out the numerator. The numerator worked out to be, if I'm not mistaken, the numerator worked out to be this value here. So actually this becomes n times the sum of the xy's minus the sum of the x's times the sum of the y's all over n. That's our numerator. And our denominator is going to turn out to be, it's the square root. Okay, well, the sum of squares for the x's, where has that gone to? The sum of squares for the x's is this term here, so it's n times the sum of the x squareds minus the sum of the x's to be squared all over n. That was the first one. And then the sum of squares for the y's is n times the sum of squares for the y's minus the sum of the y's all to be squared over n. And it's the square root of that. Okay, keep an eye on that. This gives us an n squared here. Okay, that's going to be an n squared. Okay. And then we get the root of it, okay, which brings it back down to n. So actually this becomes n times, I know this looks like it's getting very messy here, but it's going to bring us to a stage where this formula is a lot handier to use, okay. So now we end up with n times the sum of the xy's minus the sum of the x's times the sum of the y's all over n. Okay, and this thing here, okay, is going to be the same as all divided by, okay, it's the square root of n times sum of the x squareds minus the sum of the x's, all to be squared. It's that thing here. Okay, that's that. It's the square root of a over b is similar to the square root of a. And then similarly over here, times n times sum of the y squareds minus the sum of the y's, all to be squared. It's that, which needs to be divided by the square root of, well, n times n is n squared, so the square root of n squared. And you can see what's going to happen when we invert this fraction. Okay, this becomes n times the sum of the x y's minus the sum of the x's times the sum of the y's divided by, and it's this term here, n times the sum of the x squareds minus the sum of the x's, all to be squared. That term times n times the sum of the y squareds minus the sum of the y's, all to be squared. Okay, and it's the square root of that. Okay, and the square root of n squared is n, and we have an n here. When we invert this fraction, okay, our n's cancel out, which gives us our next form of our equation. Okay, which is this is form 3. Okay, of where we wanted to get to. Okay, now what's good about this particular equation here, okay, is that when it comes to its calculation, you just need to calculate an x squared values, y squared values, and the cross products. Okay, whereas when you use this form of the equation here, okay, you're going to have to calculate x minus x bar terms, y minus y bar terms. You're also going to have to calculate x minus x bar square terms and y minus y bar square terms. So actually there's 4 fundamental calculations going on in here, okay, and also the means of the x's and the means of the y's. Okay, so there's 4 fundamental calculations and 2 means going on in here, whereas with this there's only calculating the cross products, calculating the x square terms and the y square terms, because you've already got the x's and the y's. So this form 3 is very good from a calculation perspective, if that makes sense. Okay, so guys, once again, this was Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland, and I hope that this video, which was just trying to rationalise and show that when it comes to the correlation coefficient, okay, that there's many different forms of that particular equation, and sometimes there's different times when we want to use one form over another form, but that the equations mathematically are all the same. Okay, and that's the important thing that we're trying to get across here, is that mathematically that the equations are exactly the same, and we will arrive at the same answer. Okay, so once again, guys, thanks for watching. I hope that this video was intuitive, and more importantly, I hope that was helpful for you. So thank you. Okay, bye bye.